Hello. In this video we're going to look at solving a trigonometric equation, specifically a cosecant equation with a kind of a complicated angle. So here's the process I used to solve trig equations. When the argument or the input for the trig function is a little bit complicated, I go ahead and do a substitution. You don't have to, but I think it makes it a little bit easier to see what you're working with. Then I use algebra to isolate or solve for the trig function. Then I undo the trigonometric function with an inverse trig function. I let the calculator find the first solution for me. Then I use my knowledge of the unit circle and I find the other solution. And then I write all solutions, the infinite solutions, using k as an integer to capture the infinite solutions. And finally I resubstitute, if I substituted in step one, and I solve for the specific variable. All right, we're going to look at this specific equation, y equals cosecant, quantity 2x minus 4, quantity minus 5, and I'm going to solve it for where is that equal to negative 2, so that y value would be a horizontal line at negative 2, and technically if I solve for all solutions, and this went on infinitely, I'd be finding this one, this one, this one, this one, this one, this one, and so on and so forth in infinite directions. All right, so let's go ahead and set that up. So if I have cosecant 2x minus 4 minus 5 equals negative 2. First I'm going to do that substitution. I'm going to let theta be 2x minus 4. So now I can rewrite cosecant of theta minus 5 equals negative 2. And that's a lot easier to work with, just to see. Now I want to go ahead and solve for the trig function. In this case it's not particularly complicated. I'm using algebra. Since this is a subtraction by 5, I'm going to add 5. And I've already isolated my trig function. And here at this point, theoretically, I would use an inverse trig function. Now I say that because it's not going to really help us out, but I'm going to show you why. So technically, theta is the inverse cosecant of 3. The problem with that is, when you look at your calculator, you see that you don't have inverse cosecant when you look at your trig buttons. So what you have to do instead is change cosecant into sine, right? A form of sine. So I know that cosecant of an angle is the same thing as 1 over sine of that angle. Now, I want to solve for sine. So I'm going to multiply both sides of the equation by sine of the angle. Right? And then I have, let's just say 3 sine theta. And here I'm going to divide by 3, so I can finally isolate the trig function. And now I can take the inverse sine of both sides. And finally, I've solved for the angle, and in a way that I can use my calculator to actually give me an answer. Okay. So, here I do have an inverse sine button right there. So I'm going to do second sine, which would access the inverse sine. And then 1 divided by 3. Let's see if that'll come into focus. There we are. Whoop, almost, not quite. Had it for a moment. Well, it's hard to see. Usually it comes into focus a little bit better than that. But it's 0.33984. Okay, 0.33984. Sorry about that, it just won't go into focus right now. So you can do that on your calculator. You can pause the video and just verify for yourself that that's what we have. So when we were solving for theta equal to inverse sine 1/3, calculator gave us that theta is 0.33984 radians. I'm in radian mode. All right. So now I have found the first solution, which is that calculator solution right here. So I've undone the trig function using an inverse trig function. I found the calculator solution, the first one. Now I need to find the other solution that the calculator can't find for me. But remember, what this question is asking is for what angle, and it's understood you can only look, because of the theoretical restrictions, between negative pi over 2 and pi over 2, is, since we're talking about the sine function, we're looking at the y-coordinate. Is the y-coordinate a length of 1/3? Okay? So, if I look at my unit circle then, what I can see is the calculator told me 0.33984 radians, so somewhere in here. And what that says is that basically for this location on the unit circle, excuse me, you have an associated x-coordinate and y-coordinate. The y-coordinate is a length of 1/3. Okay, so that little red line there, that vertical line, has a length of 1/3. So the question then is, where else on the unit circle is the y-coordinate a length of 1/3? Excuse me. Well, we can see in quadrant 2, right about here. And so you'd have another angle here where we're looking for this angle, right, this rotation. Now, how do I name that rotation? Well, what I can think of it as is rotating to pi and then back this little bit of theta. Well, this little theta is 0.33984. So essentially, this angle is pi minus 0.33984. Excuse me. So that would be 2.80175 radians. Okay? Now that means what I have then, if I now talk about infinite solutions, right? That's the third part I want to do, part C. So I found both solutions now. Now I want to find all solutions using k as an integer. So I have theta equals 0.33984 plus essentially 2 pi k. What I mean by that is, once I'm on this solution, if I go around the circle, which is 2 pi, I'm right back where I started, and so therefore the y-coordinate is 1/3 again. But now I have a different angle, because I rotated a different amount. And if I'm here at my solution and I go 2 times around the circle, I'm back at the same location, right? Coterminal angle, and the y-coordinate is 1/3, so I have another solution. And then I could go negative 2 pi. So as long as k is an integer, k equals 0, 1, 2, 3, or negative 1, negative 2, negative 3, that's how many rotations I'm going once I'm on that angle. Now most people will write that as 0.33984 plus 2k pi. That's just a little bit prettier. Okay? And the other solution is 2.80175 plus 2k pi. Now that's what I call my generators, meaning they'll generate all my infinite solutions. But we're still not quite done. We've found theta, right? We have not found x. So here's where we have to resubstitute and then solve for x. So let's take a look at then. Remember, we let x be theta be 2x minus 4. So since I have theta equal, let's put this here, 0.33984 plus 2k pi, and I also have, let's take the other color, theta equal to 2.80175 plus 2k pi. I've got to go back and say, oh, but theta was 2x minus 4. So here we have 2x minus 4 equals 0.33984 plus 2k pi. And again here we have 2x minus 4 equals 2.80175 plus 2k pi. Okay? So here's where we're going to solve specifically for x. All right, now, let me just kind of do this so we don't confuse things. Now, this is the reason we stay in radian mode. We solve these because it's at this point, we know this is in radians. 4 is 4 radians. When I add 4 to both sides here, I'm adding 4 radians. If you had solved originally for theta in degrees, you'd be adding degrees with radians, and they're obviously not even the same type, unit of measurement. They're completely different. So that would cause a problem. Okay, so here you have 2x equals 4.33984 plus 2k pi. Now, why did the 4 not affect the 2k pi? Well, because k is a variable. You have to add like terms. This isn't 4k, it's just 4, so you can add numbers with numbers. And now, let's see, we have x, let's divide by 2, right? 4.33984 divided by 2 plus 2k pi divided by 2. Now the 2, of course, is going to affect everything, right? So here we're going to get x equals 2.16992 plus k pi, all right? And then doing the same thing over here, I add 4 to both sides. I have 2x equals 6.80175 plus 2k pi, right? And now I divide by 2. X equals 3.400875 plus k pi. Okay? Now, if we had been asked to solve this equation in the reals, meaning I want all solutions, this would be your answer. This here and this x and this x, and you would tell someone, well, k is an integer, so you can just keep putting on substituting integer values for k, and you get everything you need. Okay, so that would be in the reals. Now, let's say we're asked to solve for this here, but only an interval. We only want some solutions, not infinite solutions. And let's say we want to go from 0 to 3 pi. Well, 3 pi is a little over 9, right? So let's say about 9.4, we'll just say approximately. So what that means is I'm looking for those x values that are solutions, right? But only between 0 and 9.4. So on your graph, here that means we wouldn't be looking at the graph anything less than 0 and anything more than 9.4 or so. So now we're only looking for those solutions where y equals -2. So that would be this one, this one, this one, this one, this one, this one, and most likely not that one. But we'll find out. Okay. So let's go ahead and do that so you can see what that looks like. Okay. So here, if I let k be 0, then what you do is you put 0 in here, and that's gone. So you just have x equals 2.16992. If k equals 1, then x is equal to 2.16992 plus 1 pi, so about 3.14 added to this. And when you do that, you'll get about 5.31151. Now, when I need to ask myself as I'm getting my x values is, do they fit between 0 and about 9.4? Yeah, that's good. That one's good. Now let's go to k equals 2. So I add another, 1 pi. So x would be, so this would be 2.16992 plus 2 pi, right? And I'll get 8.45311. And that's less than 9.4, so I'll take that one. Now when I put it k equals 3, I get 11.59470. Now that exceeds 9.4, right? I wanted to stay less than 9.4, only between 0 and 9.4. So this one I don't want to take. I'm done. So now if I keep increasing k, I'm just going to get bigger numbers, so I don't want that. So now I'm going to try some negative values of k. And if anything less than 0, I'm not going to take. Well, I know that all I'm doing is adding or subtracting pi, so I know if I subtract about 3.14, I'm already going to have a negative number, so that's not going to be a solution I want. But let's go ahead and just figure it out so you can see it. When I do 2.16992 plus a -1 pi, I'm going to get x equals negative 0.97167. And again, we don't want that one because that's less than 0. We do the same thing over here. I think I'll make these in red, so we're going to do that. We're going to show in color on the graph. So here we're going to do the same thing when k equals 0. I just get 3.400875. And then when k equals 1, I'm not sure why I went 1, 2, 3, 4, 5. I don't know why I went 6 decimals there. I probably would have gone 8, 8. But anyway, for k equal 1, you'll get 6.54247. So this is good, this is good. If k equals 2, I get 9.68406. That's already past what I want. Now we'll go try the negative k's, like negative 1. And we'll get the x, this is what x equals. So x equals 0.25928. So I want that one. When k equals negative 2, x is negative 2.88231. Right? And that one is too negative, right? So I don't want that one. So again, all I'm doing is putting in values like k equals 0, k equal 1, k equal 2, and then k equal negative 1, k equal negative 2. And you can just verify this, pause the video and verify it. Now, let's look on the graph and see what's happening here. So, we're trying to solve for where this graph is negative 2. And it looks like, if I look at the solutions on the left-hand side, which I did in black, when k equals 0, I got a little over 2. So when I go over 1, 2, and here's this is what I found, this solution, right? Then the next one, because I add pi, you can think of as adding a little over 3. So you go over a little over 1, 2, 3. So I'm picking up this solution, right? And then I add about another 3, right? Because I'm adding another pi. So let's see here. 1, 2, 3. It's picking up this one. Right? And then we don't have any more work on that side. So this was k equal, for this generator, k equals 0, k equal 1, k equal 2. And then k equal negative 1 put us on this solution, right? We could see we'd go negative 1, 2, 3. And you could see on the wave, it's on the left side of the U, if you will. So this generator, the 2.16992 plus k pi, is generating all the solutions that are on the left side of the U, right? It would pick up this one if you put in k equal 3, and so on and so forth. If you went k equal negative 2, you'd get, so this would be k equal negative 1, k equal negative 2 would be about here, okay? And then these, on the right-hand side, for k equals 0, we got 3.4 something. So we're here at, let's see, 1, 2, 3. We're picking up this one. K equals 0 picked up that solution. K equal 1, let's see, you added 1 more pi, so you'd be at, let's see here, 1, 2, 3. That's this one, right? And you'll see k equal 2 will pick up this one, right? And that one, I'm sorry, was not one that we wanted, so we don't want that one. That was exceeded because we were at 9.4 because we wanted to be up to 3 pi. But then we had k equal negative 1. That one was this one, okay? So you could see this generator was picking up all the solutions to the right, on the right side of the U, except this one, I'm sorry, I kind of exceeded it. It was 9.68, which was beyond our interval. But you can see the idea of what's happening, right? So that is what we're talking about here with the k's, how you pick up infinite solutions, and that concludes this video. Thank you so much for listening.